close to designing such a thing. So my name is McDonald.
And I'm Zack, Goodlin, and we're electronics students here at the University of Arkansas Fort Smith.
We just want to take a second to thank all of you for first of all, being here, and second of all, giving students like ourselves a platform to share the projects that we've worked very, very hard on with our professors and other people. So thank you again for that. So today we're going to talk about the design process, how we kind of came about to actually get to this finished product, as well as we're going to talk about how we see it being used today and in the near future. And then we're going to talk about kind of the nitty-gritty of how it actually functions, so you have a better idea of how it works. So if you wanted to use it yourself, it'd be easy to do. So we started in Dr. Hahn's class, actually, an introduction to programming. It was my first semester of the Electronics Technologies Associate's degree, and I knew nothing about anything. And at the beginning of the year, I came in just completely green. And through that semester, Dr. Hahn actually gave us a really great foundation of being able to structure code properly, debug, and all that kind of stuff. And we were actually able to use that and go far beyond the class to achieve the goal of this project. We started with the idea of temperature and reading a sensor, having a Pi do something. And over a period of time, we kind of eventually settled on the idea of temperature and reading temperature and doing something with that. And so that is how we came up with our original prototype, Thermal Outlet 1.0. So as you can see, it's very, very rough. This was put together, as low budget as possible, and this black stuff right here, that's actually not a solid material, that's tape. So whenever you actually plug something into the receptacle, it actually would flex down, and it felt very, very bad to use, and it felt like you were going to pull everything apart when you unplugged something. It just wasn't very good. So then we moved on, and when we were preparing for the symposium, we were like, we want to make this as good of a project as possible. So that is where we came up and we designed this. This box is 3D printed. It has, the Raspberry Pi is mounted inside the casing very securely, so you can plug and unplug everything that you need to very easily. Has a reset button on the side, which allows you to restart the program if anything goes awry. And it also has an LED to indicate if you have power going to the receptacle or not, so that you don't accidentally shock yourself when you expect it to be off when it's actually on. So this was our kind of like, we transitioned from a really rough design to this, and it took a lot of hours of preparation, and we actually we had someone design the actual box, and then we 3D printed it ourselves. And then we also went from our original control board, which was very rough again. We actually wanted to make this look as good as possible, even though it wouldn't be seen. And so we decided to design a PCB, which is a control board, which is what you solder things to. So we started with a schematic. This is actually Zack's design. So he took our original control board and put it all in this schematic, and all of the details that are here is what went into our PCB. And then we actually had that PCB manufactured, and this is what it looks like. So all of these labels, so that everything is easy for you to solder and know where everything goes. This is with all the components soldered to it. So we have resistors, we have our transistor, which we'll talk about more later, an LED, that's the LED that indicates whether or not the outlet is hot, or the receptacle is on or not. And then we're going to talk about now, why does this project even exist? Where do we see it being used today? We're going to talk about a few of the reasons of the many, because it's a very broad array of uses for it. So first one, we could attach multiple sensors to the box and have it control a large number of rooms in a house. So for instance, you wanted to have a bathroom warmer than your bedroom. You're like me, you like to sleep with the covers nice and tight around you, stay warm. You can have multiple sensors and be able to regulate things at different rooms to be different temperatures. As well as sous vide. Sous vide, that was our original design use was for it to be a sous vide machine, and that is just cooking using a steady temperature all the way for a long period of time until something's perfectly cooked. And they're actually quite expensive, and they're only used for cooking. So we start here. This one's pretty popular, $90 though. Amazon recommends it. It's got a lot of reviews. Then you move up, you want something nicer. A lot of people like it again, 1,500 reviews, 4.5 stars, but still $200. And then if you want something really nice, you're looking at almost $450 for a cooker. See, our outlet is far more versatile. It only cost us $54 to make this as a prototype. If we decided to actually try to have this manufactured, that price could drop dramatically. Especially if we didn't 3D print the box, we used an actual manufacturer, that price could drop dramatically. The PCB could drop as well per cost. The sensor would drop as well. All of these prices could drop dramatically to even decrease our price even more to set ourselves aside from our main competition. So also one other thing, I like to really think about this, because this is a personal use that I would see myself using it. If you ever have like a room that's really cold and your heater's out or something like that, you can buy, you pull out an old space heater. And so usually with old space heaters, they don't turn on and off depending on the temperature. So you could plug it into our outlet, you can turn on our outlet, and based on the temperature, without having to get up and unplug and plug back in the space heater, you can have it maintain a constant temperature. So now that we've talked about a little bit about why and how we see it used, we want to talk about how it operates. And we're actually, before we talk about how it operates, we're going to actually show you it in actual use.
So, we're going to use this as our space heater because we do want to bring one. And let's see, we have it plugged in. Now, when you plug in the power, you need power to the actual receptacle. It's kind of like a power strip in a way. You have power extended out. It's just controlled by temperature. Let's see. We have water. We're just use water that has ice in it because it's really cold, and so it actually does work. So since this is cold and this is room temperature, I think we have it set at like 80 degrees right now. So we're gonna stick it in here and let's turn on that heater. Definitely not easier. Yeah, real cold. Yeah.
So as this sensor heats up, the program is actually running right now, and it's determining if the heater needs to stay on or turn off. And at a point near the future, it will sense that it's at the right temperature and the heating element needs to turn off to maintain that temperature. So as this would stay, you can put it back in, cool it back down. It senses it needs to turn back on, so therefore it turns back on.
Heat up again. This is waterproof, so you can use it for cooking as well as actually in the room. This is not a very powerful heater. Yeah. Last minute.
So now let's move on and talk about the actual program that makes all of this, work. Oh. So we have two parts of our program. We have our server and we have our client. Our client is the actual menu that you would select on a PC that would be remote to the server, which the server is the box. It would be, so you actually have a graphical user interface that you can select temperatures from, otherwise known as a GUI, so just a menu, whether that be room temperature, 72 degrees, you want to cook a certain type of meat, that can be predetermined, 160 degrees, depending on what your need is. But that information has to be sent somehow. So we have to send it from the from the client PC to the Raspberry Pi to actually be processed. That we accomplish with networking. So networking is actually something we didn't talk about in our class. Actually, approximately 80% of our code, we actually had to go outside of what we learned in class. to be able to do. So like networking, threading, the actual graphical user interface, but everything was built on the solid foundation from introduction programming. So the way that kind of networking works, I'm going to just kind of go over it briefly, is so you have a client, you have something that needs to be sent, but how does it get there? I think a good way to demonstrate why you have to be specific and how you code it is I can't just go, hey Zach, I want you to meet me in Houston, let's do it. He can't just go to Houston to meet me. There's a few more questions he needs to ask and a few more pieces of information he needs to know. Like, what part of Houston? What's your address? Like things like that. So the wireless network, that's our big picture. That's meet me in Houston. The server IP, that's his actual address. That is where exactly I need to meet him. And the port, that's what allows the information to actually travel. So that's kind of our road that allows the data to be transferred. Another thing is we can't just transfer data due to the fact that it's you can't just have your data just going through the airwaves free and open. So we have to encode it. The coding we used was UTF-8. It's just kind of a common type of code. It's actually very secure in how it travels. Certain types of data aren't very secure. Like this makes sure that the server receives it, and there's other types of data that just kind of throw it out there in hopes that the server will receive it. This is guaranteed to get there. So that's the kind of the client, how it sends the data. Now I'm going to talk about the server and kind of how it receives the data. But before I talk about the server, I want to just kind of describe threading, which is what we had to do to be able to control both our networking part of our process of our program and our temperature control. We had to be able to do both simultaneously so that we could update the temperature multiple times and be able to control the temperature continuously. So threading kind of works like, if you think about it, you have two processes, two programs working in parallel under the umbrella of a whole program. And as you know, parallel lines never intersect. So these programs can never talk to each other. And I'll explain how we get them to talk to each other in just a second. But they never intersect, but they're always running at the same time. So in our networking process, we have it looking for a temperature from the server or from the client to be sent. So it's looking to receive that information, and then once it receives it, it decodes that information back to regular numbers like 165 or, for instance, quit if you wanted to close the program. And then in the temperature control, we have it reading the temperature from the sensor, like if it was too cold or too hot, and what it needs, and then also, depending on that temperature, it makes the decision to turn the outlet on or off. But like I was mentioning earlier, they have to be able to communicate. Two pair of lines never intersect. How do we get those two things to communicate? We use something called the queue. The way I kind of also like to look at the queue is it's like having a toolbox. If you have a tool, you get through using it, the network, it has a tool, it gets a new tool, it gets through using it, it puts it in its toolbox or the queue, and then the temperature control, if it needs something new, if it sees that there's a new temperature that's been added, can go and get that temperature. The other thing that's nice about the queue is, let's say for some reason you needed to program 5 different temperatures and you needed it to remember all 5 of them. It allows us to be able to what's called buffer, and it allows us to kind of stack things one after the other, so like 1, 2, 3, 4, and 5, turn it into an actual queue, like you would get a number in a line. And that is how those two things work together. So the biggest thing is like we have information sent from the client to the server gets that information, it takes it, it decodes it, and then it puts it in, and it allows it determines if the outlet needs to be turned on or off depending on what the temperature is at right now. So now that I've talked a little bit about the program, I'm going to toss it over to Zach and let him tell you about our awesome hardware.
Thank you, Luke. You look at our box, our thermal controlled outlet. It's in its name. We have an outlet. That's what we use. It's just a a common way to facilitate power. Now, on the inside, we have a solid-state relay. Now, a solid-state relay is not like regular relays where it has a moving arm. This instead has a sensor and a light beam. That the light beam turns on the sensor, and then that in turn switches it on or off. We also have a Raspberry Pi 0W. Now, we needed the W, which means wireless, for our networking and our communication between the computer and the server. And so that's why we used this specific Pi. And it was cheaper. We could build it at a lower cost. It does everything we want to, including you can code and program it. I think Python comes.
It comes with Python actually pre-installed already.
Yeah. So it was a really awesome choice for us. Now we also have our temperature sensor. We chose this one because it has super high range. It's like anywhere from 0 to, I think it was above boiling. Yeah. So it's also waterproof. It's an excellent choice for our specific project. Now we have a 222A BJT amplifier. Now a BJT is basically a switch. So this is a low power amplifier which takes low voltages and low power and switches them on or off. And I'll get some more about why we needed this in a minute. The relay. I can do that. Yes.
Oh, you did my bad.
So the relay, I mean, I can do it again because I think this was the coolest part. Personally, when I went to look for them, what did I want? There were so many options out here for relays. I chose this one because it's quiet, it doesn't make any noise, it lasts a super long time for constant switching. And that's kind of what you need. You're going to be, if you're cooking, you're space heating, it's going to be left on for long periods of time. So this one, the relay, was specifically chosen. I went out there and looked for it, and this is what we came up with. Now, how do they all work together? So, I mean, you have it all, you've seen it work, but this is how they actually interact with one another. You have your temperature sensor, it's receiving data from its surroundings, like the air or the water, and it's going to send the temperature to the Raspberry Pi. Now, the Pi is already receiving the server information of what it actually wants to be at. So let's just say we had it at 80 degrees. We wanted it at 80 like we did, but it was above 80, like as if it was in front of the heater. So it reads it, it's going to compare the two in our program, and it's going to send the information it needs to the transistor. Now, our transistor is a little switch that turns on our big switch. You can kind of think of it as a ceiling fan and a ceiling light with a pull cord, and you have a switch on the wall. The relay is our ceiling fan, to where you can't turn it on unless you have your little switch on, so your switch on the wall. So our transistor, once it turns on the big relay. So the Pi will send a 3.3 volts to the transistor and turn on the relay. Now I had to use reverse logic for this because our relay is a normally on relay, which means when there's no power to it, it's actually conducting. So we had to, this was a big issue that we had to overcome in the beginning of our process of development. Because at first we were just thinking, oh, we could just trigger the relay with a Raspberry Pi, and it actually didn't. We needed 5 volts, as you see here, for our relay. It needed the current of the 5 volts. So we used the transistor in a way to switch on the 5 volts, which then switches on our relay. If it was 80 degrees, temperature sensor reads it's above 80, it needs to switch off. It's going to send that 5 volts, open up our conducting line, and turn it off. And therefore, our thermal control outlet is off, and that's what you saw presented.
And so one other thing to that is, so that actually had to flip our logic in the program. So when actually in the program you read it, when it says it's equal to or above temperature, it actually says turn relay on, which would usually turn the heating element on, but because of how we have the hardware set up, it's reverse engineered to where it turns it off. And then vice versa, if it's below the temperature, it actually sends the message turn off the relay. And so we just think that's a very interesting thing that we actually had to overcome and think through. So now we'd like to open it up to any questions that you might have.
So as you were working through this project and kind of designing your prototype, what was the one issue that you struggled with the most that you had to do kind of more extensive research on?
I would probably say our networking. Getting it to communicate wirelessly. That's actually, so that's an interesting story. I was talking to a friend of mine he's actually graduated now, but he did an internship in ExxonMobil, and they were using Python, and he was working in a team, and he had a problem that he had to use networking, and he was talking with some graduate level students, and they didn't even know how to use networking in Python. And so it was one of those things, there's not a whole lot of information on it, and so that was one of our biggest goals, because you had to, with not a lot of information out there, you had to use it in kind of a special way. And so that was probably our biggest, obstacle to overcome. And yeah, it works great now.
Yeah. So you built now custom PCB.
Yes.
And aside from your kind of homemade, how hard was it? Like how to make this the PCB? You have to come up with find the right appropriate program, right?
Yeah.
The schematics, and then you have to put it into like a rubber file. All the process, was that easy or was it difficult?
We worked on it together. I did kind of the design process. I think it wasn't difficult. It just took a second to kind of like figure out what we wanted to do, because we had like our original PCB from our like original sketch schematics, and it was kind of like difficult to process them because we were kind of just trying to figure out what we wanted at the time, and we had added other things. So when we actually sat down and I was going to design the actual schematic to which you would convert into a PCB, whatever, different Gerber file, and then it would convert it to a PCB to where you could set it up. That took a bit, took some time just to kind of figure out what exactly we wanted, how we wanted to put it on the board, how we wanted to actually. I think we made it to actually connect to the Raspberry Pi. You saw like the pins, the long row of pins. That's how it connects to the Raspberry Pi. So that was in our mind at the design process. So I mean, it took some work. It wasn't overpowered. It was unbelievably hard.
I think one thing that made it easier was our foundation, because we've been in the Zack's he's almost through with the electronics technologies program. In the classes that he's taken, we've actually never learned anything about design, but our professors have done such a good job just teaching us and allowing us to understand what each component does, that Zack was able to with that knowledge put it in put it into application, and so he's being modest. For most people, designing a PCB would be very difficult. We actually made it very, very small, so I mean it's about a third or a quarter of the size of a credit card. So the PCB and the Raspberry Pi both are very small and can fit very easily, and we can actually make the box smaller as well. Anything else?
Good question. What's the maximum amount of time this device can run continuously without experiencing a hardware malfunction or failure?
So actually we were testing that the other day, and we were running it for over 2 hours, and we didn't have any kind of issue. So we don't anticipate it having any type of issue for a long period of time, especially if it's actively like having to control temperature. So like if you're cooking sous vide, for instance, or you're using it like a space heat, using it to keep your room warm, because it's actively having to switch that temperature, the program is going to continue to run on the Pi. And even if it stops working, all you have to do is push that button. It reboots the Raspberry Pi, and we've actually made it to where the program runs whenever the Pi boots, so that all you have to do is plug the Pi in, the program starts, and you're good to go.
It takes 1 minute to reboot, and it's working properly again, even if you had a malfunction. So it's not a long wait. It's not like a lot of downtime or whatever. It's just an easy button push, reset. Everything will work properly in a minute.
So if you're cooking something, you can just unplug your heating element, allow it to reboot, and plug it back in, and you'd be good to go. Well, thank you all for coming. We really do appreciate it. We were very excited to give this presentation. And again, thank you for giving us this platform to share the hard work that we've really put into this and listening. So thank you again.